So the combined gas law takes a look at our ideal gas law and says that if we have a constant number of moles, and remember we have R as constant, what happens if I have changes in the pressure, the volume, and the temperature? What if they all change? What happens if I'm not just changing one variable, but I'm changing two variables instead of one? So the combined gas law is P1, V1 over T1 is equal to P2, V2 all over T2. What do we have? We've got, let's see, what are the different laws that we can look at? We've got P1 times V1 is equal to P2 times V2. That's Boyle's law. We've got, let's go to green. We've got V1 over T1 is equal to V2 over T2. Now that's Charles's law. And last, we've got, let's go to purple. We've got P1 over T1 is equal to P2 over T2, and that's Gay-Lussac's law. So it's a combined gas law because we're looking at all three of these laws together. And we're not looking at Avogadro's law because the number of moles is constant. We're not changing the number of moles. All right, so let's take a look at this problem. And you know that you're going to be using the combined gas law when you see more than one unit changing. So let's read this problem, and then we're going to take a look at what's changing. If I have 2.9 liters of a gas at a pressure of 5 atmosphere and a temperature of 50 degrees Celsius, what will be the temperature of the gas if I decrease the volume to 2.4 liters and decrease the pressure to 3 atmospheres? So what do we have? We start with 2.9 liters, which is a volume, at a pressure of 5 atmospheres with a temperature of 50 degrees Celsius. Well, what is actually changing? We're changing to 2.4 liters, and pressure is going down to 3 atmospheres. All right, so we see that we've got two different units that are changing, and that's going to be our pressure and our volume. All right, and so we need to find our final temperature. So let's write down what we're given. Oh, I'm still in purple. That's fine. So P1, let's say, is 5 atmospheres. V1 is equal to 2.9 liters. And T1 is equal to 50 degrees Celsius. Let's go ahead and change that to kelvins right now. 323 kelvins. And what else do we have? We've got that our P2 is equal to 3 atmospheres, and our volume 2 is 2.4 liters. All right, so let's see what's happening. Our pressure is decreasing, and our volume is also decreasing. So we're decreasing the pressure and decreasing the volume. Now we want to know what happens to our temperature. All right, so if we were to take a look at, what are we looking at? If we take a look at Gay-Lussac's law, if our pressure decreases, then our temperature should also decrease. And if we look at Charles's law, that if our volume decreases, then our temperature should also decrease. So we should suspect that our temperature decreases. That's what we suspect, that our temperature should also decrease, right? Because P and T, that is a direct relationship, and V and T is also a direct relationship. So let's take a look at what we have. P1, V1 over T1 is P2, V2 all over T2. And we're looking for T2. So this is another one of those tricky, let me move this over so I have more room. This is one of those tricky problems where you've got to do a lot of moving things around. Let's start over here. P1, V1 over T1, P2, V2 over T2. And we're solving for T2. So first we've got to get T2 not in the denominator. We need it in a numerator. So notice here that these two cancel out, and I end up with T2 times T2 times P1 times V1 all over T1 is equal to P2 V2. Right? I'm going to move over to the left now so we'll have more room. All right, so I still want to get T2 by itself. So remember we did before, we had to multiply by the inverse. So I'm going to multiply T1 over P1 V1 to both sides. Right? So let's see what cancels out. Notice our T1 over here cancels, P1, V1, and I'm left with T2. Okay? So T2 now, right, all the way over here, is equal to P2, V2, T1, all over P1, V1. Now let's just plug and chug. Okie dokie. So I've got 3 atmospheres times 2.4 liters times 323 kelvins, all divided by 5 atmospheres times 2.9 liters. Our atmospheres cancel, liters cancel, and I'm left with, let's say I've got 160.39 kelvins. Let's convert this back into Celsius. So I have to subtract 273. That gives me negative 112.61 degrees Celsius. But if we look back through our problem, we've got 2 sig figs, 1 sig fig, 1 sig fig, and 1 sig fig, and 2 sig figs in our numbers to begin with. So our answers have to have only 1 sig fig. So we'll say that this is, approximately 100, negative 100 degrees Celsius. So, does our answer match what we thought? Our temperature goes down. We started with 50 degrees Celsius. Now we end up with minus 100 degrees Celsius. So our answer makes sense based on what we thought we should get in the beginning.